Testing. Okay, I think everyone seems ready to start. Good afternoon, everyone. So, one very important thing we need to settle first. So next Thursday is a holiday, so we have to have a replacement. So when are you free? When's your schedule free? Could you check? Huh? Friday. Friday? Huh? Friday not free. Okay. How about today? Today? Before? No. No. Huh? Okay. Huh? Thursday morning. Yeah, today, right? Today morning. Thursday morning. You can't. Monday afternoon? Okay. Monday afternoon? Okay. Sorry. How's what FYP? How is your FYP? From what time to what time? Oh, 6 p.m. to 9 p.m. We do afternoon, right? Monday afternoon. So maybe 1 to 3? Huh? No? After 2? 2 to 4? Huh? Monday 2 to 4? Okay. So next Monday. How about next Monday 2 to 4? Next Monday 2 to 4. Okay. So what's the date for next Monday? Huh? 25. 2 to 4 p.m. Okay. Okay. 25th of 9 to 4 p.m. Okay. Yeah. Okay. I'll try and book a room and then I'll let you know. Okay. On next Thursday replacement class. Okay. Okay. Another thing is I already fixed my office hour. So it's on Wednesday 10 to 12 and Fridays 2 to 4. Okay. So you can message me before you come. Then I'll be in my office. And I promise that I will talk about the project one today. Okay. So project one, you need to write a report. Okay. At least 1 full page. Okay. This is about your content. 1 full page. So maximum is 3 pages. And what do you need to write inside your project? Let's see. So your project structure should have some introduction, setup of the theory, and example of the theory. Okay. So you introduce a theory and then you show us how this theory being used in mathematics. Okay. Give 1, 2 examples, and then you put a reference. Okay. Bibliography. So what kind of theory I'm interested? You are interested? You should write on. So for example, you can write about some famous result. Okay, so this project is about topics in calculus 2. Okay, so while I go through some theory, I won't prove it in details, okay, because it won't be tested. So if you are interested to know why they are true, okay, then you should go and look for it and prove it, okay. So you can put some famous result, okay, or while you are doing exercises or while I'm teaching, you thought of some interesting properties, okay? Some properties that you never see in books, okay? You try to prove it or disprove it, okay? Also work. And next is some foundation. So it's like background theory used in reading calculus. For example, we didn't introduce what is numbers, real numbers. Okay, so but whenever you do calculation or using theorem, these properties are keep used in your lecture or your content of your course. Okay, for example, the density of real number, the completeness of the real number, the construction of the real number. So how does real number appears? Okay, so why we can draw real number as a line? Okay, why is it not discrete? Why is it not like the natural number or integer? They are discrete, right? But why real number we can join as a line? Okay, we didn't touch this in our course, so you can try to look for it. These topics are the density of real number, completeness of real number, and so on. Okay, so if it interests you, so you should go and look for it. Okay, so why I set this project? So first is to explain the theory in details and efficiently that makes sense to another students of the same year when reading the document. So okay, so the level you wrote this document have to be comprehensive by the other students here. Okay, so either when your friend look at your document, he or she should benefit from it. Okay, he or she should learn something from it. Okay. Two, so build your personal interest towards a specific subject. Okay, mathematics subject. So if you are interested in this question or segment or topics, you should go and look for it yourself. Okay, so develop your personal interest. Three, to fill in the rigorous gap in the theory presented in lecture. Okay, so this is what I mentioned last time. So I didn't prove it. For example, it required epsilon delta definition. We don't use, we don't prove. You can try and prove it in your project. Okay, and to learn to find and read mathematical reference and research paper. So you have to learn how to find references to the subject that you are interested in. Okay. Nowadays, internet is very convenient. Okay, you can just search online. If you have problems searching the reference, you can let me know, and I will let you know how to find. Okay, and then the marking. So first project will be 10%, second project 10%, and then presentation 5%. Okay, so for this 10% here, I will divide into three categories. So one is language, one is completeness of your presentation, one is difficulty. Okay, so language, I look at your grammar and your clarity of your arguments. And completeness of the presentation, meaning I look at the flow, the logic flow of your arguments. Okay, you need to do it step by step. Okay, don't just randomly pick your content. And the difficulty is complexity of your project or originality of the project. Okay, so that's why it's very important that before you choose your topic, come and talk to me first. Okay, and then I'll let you know whether it's too easy or it is too hard, or I will suggest you to do something manageable. Okay, so it is due in week 10. Okay, so you have a lot of time. Okay, throughout the lecture, if you found that something you are interested in, you can let me know, and then you say you want to do this, and then how you're going to do this, and then we'll see whether it is suitable for you or not. Okay, before you write it. And then, so before you hand it in, maybe a month or 2 weeks before, you send me a draft, and then I will have a look, and then I give you a comment, and then you can fix according to the draft, to the comment. Does it make sense now? Does everyone clear what you should need to find to do for a project? Okay, so throughout the lecture, please look around. Okay, what topic you are interested in. Okay, so first project is kind of towards pure maths. Okay, so meaning we care about theory and then how we apply in a mathematical setting. Okay, so important thing you need to know is you want to introduce a theory, okay, and then give example of that theory. Okay, how to use it. Is it clear? So for example, last time we introduced properties of limit, right? Remember last lecture? So if you're going to do that, you prove it, and then you give example. Again, like example we did our class, give a sequence and then try and demonstrate how we use the property of limit to find the answer. Okay. Any question? No. One clear. You clear on what you need to do. Okay. 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 So seems like not many of you using the forum yet. So do you have any question from last lecture about lecture content? Question? No. So far okay. Okay. So please do the tutorial I posted. I think I will post here every week. So in every week section you will have tutorial to do. Okay, please do it so that you will get used to the content. And there are answers provided behind the book. Okay, there's no solution. So if you are wondering about your solution is correct or not, you can just send to me. Okay, just ask me. Okay. Okay, we should continue. Continue. So let's pick up from where we left last time. Yeah. Yeah, I will book a room and then I'll let you guys know. Okay. So where did we stop last time? Okay. So we stopped at introducing the squeeze theorem. So we end with squeeze theorem last time. So what is squeeze theorem? Okay. So suppose there are two convergent sequence. Okay. Two convergent sequence. Both converge to the same limit. Okay. And there's a sequence squeeze between the two convergent sequence. Okay, it is squeezed between. Then we will know that the sequence that gets squeezed also converge. Okay, also converge. And moreover, we know the limit. Okay, we know the limit. The limit is actually the same. Is F. Okay, so in this sentence here, again, in the last segment here, or proposition here, there are two things you need to know. Okay, first thing, it tells you that Dn converge. Converge to where? Converge to L. And what is L? Okay, by the assumption L is the limit of the original two sequence, two convergent sequence. So the picture you need to keep in mind is this. Okay, so when we talk about squeeze theorem, the picture you always need to keep in mind is this. So you have two sequence. Okay, you have two sequence converge to the same limit. Okay, so let's call it L. Okay, forever. So let's call it L. Okay, and you got a sequence that squeezed between these two sequence. Okay, and then we will know that this sequence also going to converge to L. Okay, this is the picture you need to keep in your mind when we talk about squeeze theorem. By the way, if any one of you confused in my class, right, I suggest you to ask on the spot. Okay, ask on the spot so that I can clear your doubt. Because if you carry doubt, you won't accept my next argument, next argument. Then you will be gone for the entire hour. Okay. Yeah. Okay. So let's do an example here. Okay. So let's look at this sequence. Okay. Sine to the power 3n. Naively, what can you do? You can try and write down the sequence here. Okay, what are these? What's the term? What are the term in the sequence? Okay, so when n equals to 1, it's like sine cube 1 over 1, okay, which is sine cube 1, and then sine cube 2 over 2, and so on. So from here, can you predict anything or not? Okay, if you can, I think you're a genius. Okay, so we're gonna use the squeeze theorem. So any idea how we're gonna use squeeze theorem here? Any inequality we can introduce within trigonometry. Okay, so you can bound sine x or sine n between 1 and minus 1. Okay, so how you remember this fact here? So still, you draw the picture. Okay, you draw a picture. So what is sine graph? Yes, so sine start at zero, and then go up and get a full cycle. The peak is 1, the bottom is minus 1. Okay, so sine n is always bounded by 1 and minus 1. So is this helpful or not? Not helpful? Does it tell anything about sine cube? It is still always in between minus 1 and 1. Does anyone not seeing this? So if you got, let me write here. So if you got an x in between 1 and minus 1, right? And you take cube, is it still in between minus 1 or 1? True? Yeah. Okay. So you can check at the endpoint first. Okay. So at the endpoint, it is true because when you take 1 cube, you get 1. Minus 1 cube, you also get minus 1. Okay. How about the things inside the middle? Okay. If you take cube of a decimal number, you still get you won't increase the value. Okay, so it's still staying inside minus 1. Okay, so so this is true. Okay, and then what can we do? What we can do is we can bound sine cube n over n by 1 over n and minus 1 over n. Okay, so this is for all n greater than n equals to 1, or for all n greater than 1. Okay, so are we happy now? Why? Can we use squeeze theorem now? How? Sorry? Okay, one by one. Both side limit. Uh, this is not um that is a bit dangerous. If you take limit of inequality, sometimes it doesn't preserve that. Separate. Okay. Um. Okay. Okay. I'll comment on that later. Okay. Yeah. So what can you do? So this is squeezed by two sequence. Okay. These two sequences are they converging or not? Is 1 over n converges? Okay. Why? Sorry, show it. Function, right? Okay. So these are sequence. So you can look at the function of real variable. Okay, look at 1 over x. So since remember by the theorem, if the function converges, the function of integer value integer variable also converges. Okay. So if the function defined by the sequence converges, theorem, if the function defined by the if the function defined by the sequence converges to L, the sequence also converges to L. Okay, also converges to L. So 1 over n. Okay, so 1 over n converges to 0. Why? Since limit of x go to infinity of 1 over x is 0. Okay, limit of the sequence of 1 over n also equals to 0. Okay, similarly, we get limit of n to infinity of minus 1 over n is also 0. Okay, is everyone following? Following? Okay. Okay, so you can see that you are bounded by two convergence sequences that converge to the same limit. Okay, so by squeeze theorem, since you have a sequence that bounded by two convergent sequence that converge to the same limit, the middle sequence also converge to the same limit. Okay, so by squeeze theorem, limit of n infinity of sine 3 sine to the power 3 n over n equals to 0. Okay, any question? No? Okay. Uh, okay, how about I let you try one example? Let you try one example here. So let's try one example. Try and find this limit here. Minus 1 to the power n over square root n. Okay, I'll let you try about 3 minutes with your friend. Try if you can figure out this limit on. Anyone have any idea? No? Haven't tried? You try anything? Okay, use squeeze theorem. So how are you gonna find your convergent sequence? Okay, so you first list out what is happening, is it? So 1 over square root 1, and then 1 over square root 2, and then minus 1 over square root 3, and then you repeat the then. So to use squeeze theorem, you need two convergent sequence. Okay, to bound your the sequence that you want to find the limit. So what's the two convergent sequence here? Okay, is there any reason why you change the n to x? Okay, sure. So let's bound this to, let's check whether this inequality is correct or not first. Okay, so let's bound with just sequence, not the real function of real variable version of it. Okay, the function of the sequence. Okay, so whether is this true? So first thing you should check whether this inequality is true or not. Okay. So what do I mean by this inequality is true? Okay. This inequality actually built up by two inequality, right? Okay. So if you learn discrete math, so this is what. So you have two segment like lying inside here. Okay. So this and the other inequality. Okay. So you need to check whether these two are true or not. Okay. So you know how to check? You know how to check? Sorry. Real number sequence. Limit. Why? I mean, you just need to check this inequality true for all n. Right? It's true for all n. Okay. So each time you check, you fix an n. Right? Okay, you fix an n. So for this, so the for first one to be true, this is if and only if minus 1 is less than minus 1 to the power n. Okay. Similarly, you have minus 1 to the power n is less than equal to 4. Okay. So you need to check that this is true for all n. Okay. When n is how many cases for n you want to break the case into? Two, right? Okay. So n is odd or the n is even. Okay. Why you break into these two cases? Okay. Because you know that when n is odd, minus 1 to the power n is just n. Sorry, it's just minus 1. Okay. Because you can write n as some 2k plus 1, or which is equals to minus 1. Okay. But when n is even, okay, then n is equal to some power of 2, not power of 2, multiple of 2, okay, which means that minus 1 is 1. Okay. So minus 1 is less than equal to minus 1, minus 1 is equal to less than equal to 1. Okay, so both cases are true. So we cover everything. Okay. Yeah. So similarly, you can work out this side. Okay. Similarly, this is true. Okay. So you could imagine that you will have minus 1 is less than 1 and 1 is less than 1. Okay, use the same strategy here. All right. Okay. So we know that this the sequence -1, the alternating sequence of 1 over square root n is bounded above by 1 over square root n and bounded below by -1 over square root n. Okay. So like I forgot your name. What's your name? Zhengkan. Okay, Zhengkan. Okay. So Zhengkan says that just now he replaced n by x because he want to check whether 1 over square root n converge. Okay, we look at the function that associate to the sequence, whether it converge. Okay, I think we saw this in the first lecture, right? 1 over square root n actually converge to 0. Okay, 1 over square root x also converges. Okay, so so what can we do? So I would say, so as before, limit of n to infinity of 1 over square root n equals to limit of n to infinity square root n is 0. Okay, so we have two convergence sequence that converge to 0 bound our sequence. So by squeeze theorem again, by squeeze theorem, we have lim of -1 over n or square root n equals to 0. Okay. Okay, so I want you to try go back or in your free time, try and draw this. Okay, draw this example using the geometry. Okay, or plot out the graph. Okay, plot out the graph. Okay, and then see yourself what is going on. Okay, try and plot the graph out. Then plot the tree sequence. Then see what is really going on. Okay. Let's return to what you said just now. Can you repeat what you said just now? Okay. Before that, anyone have any question on this example here? Yeah. Oh, yeah. So what's the purpose of writing of this blue part? Okay. So this is to show that. To show that the inequalities. Oh, we have the following. Okay. So first you need to make sure it is really bound between the two convergent sequences. Okay. So before that, why we don't show? Because I assume there's a very well-known result for this, or maybe we need to invoke the definition of sign. Yeah. Okay. So in general, you can't just see roughly correct and then I write like this. Okay, you need to show why is it true. Okay, you need to show that why is it true. Okay. So let's go back to this theorem again. So what you need to check. So few ingredient you need to use squeeze theorem is first make sure that you have two convergent sequence, not just converge, they converge to the same limit. Okay, and then you have this inequality here. Okay, you have a beta sequence that gets squeezed between these two. Okay, you need to check that whether your sequence really squeezed in between them or not. Only then, okay, the squeeze sequence converge to L. Okay, because if you allow some terms go outside AN and BN, AN and CN, then your BN might not converge. Okay, you don't say that majority of my BN is lying between these two sequences, but some of them popping outside. And then these terms might cause problem. Okay, so we have to make sure that they are really in between them. Okay, we don't actually you can notice that we don't require strict inequality. Okay, we allow Bn sometimes equal to An, sometimes equals to Cn, or maybe equal to both. Okay, yeah, we don't, for example, I draw the diagram. Okay, so we allow this red dot sometimes equals to Cn and sometimes equals to An. Okay, sometimes equal. Okay, it doesn't have to be strictly inside here. Okay, sometimes it can touch. In fact, this is what happened just now. Okay, in fact, this is what happened just now. Okay, in the last example. So we jump across like this. So I suggest you to really draw the picture and then see yourself. Okay, where's the squeeze theorem doing? Okay, so go back to you. What's your name again? Yu Xiang. Okay, Yu Xiang. So just now you say we can take limit. Just now you say we take limit on both sides, is it? Take limit on both sides. Is it what you say? Yeah. What do you mean outside? Yeah. So I mean, hmm, just like you mean, you mean like this? Yeah. Do I take limit inside as well? Okay. So what is this? So what is this inequality telling me? So this just says that. So this just says that um all my sequence is bounded by 0. Is this true? Yes. Yeah. So that's why just now I asked you, do I take limit inside? So you think I should take limit inside? Okay. This is what you say, right? Yeah, take limit inside. Okay. This is what you say. Okay. So I want you to be very careful with this. Okay, very careful with this. Let me give you an example. Okay, let me give you an example here. So it's let's say we take x greater than 0. X greater than 0. Okay. And then I also take limit operation on both sides. Then what I want to do? So maybe I take x go to 0. Okay. So what do I get here? What I get is 0 is less than 0. Okay, so you need to be careful when you take limit. Okay, when you take limit on this inequality stuff, you need to be really careful. Okay, so you can't just say like this. Okay, you can't just say like that. Okay, so what we're really using is the squeeze theorem. Okay, and then squeeze theorem is not equivalent to this taking limit with inequality. Okay, so otherwise you'll get something crazy. Okay? Yeah, please take note. Please take note. Okay, so far any question or not up to here? Any question? No? Okay, let's go on. Okay, next. I want to show how useful is the squeeze theorem in proof. Okay, so let's see how useful is the squeeze theorem in proof. So let me introduce one proposition. Okay. This proposition you could use to find limit of the sequence. Okay, you could use it. So what's this segment here? So let's say you want to find the limit of an, okay, but you don't know how to prove it, okay, but somehow you know that, okay, when you take the absolute value of an, it converges to 0. Okay, maybe your sequence is jumping around plus and minus. Okay, let's look at the absolute 0 value of them. Okay, so meaning you shift everything up above the line y equals 0. Okay, and then if you happen to know that this sequence converges to 0, then limit of n to infinity of an also equals to 0. Okay, the original sequence converges to 0. All right. Okay, so let's see how we're going to use uh, squeeze theorem to prove this. Let's see how to use squeeze theorem to prove this. Okay, so like I say, right, okay, if I'm going to use squeeze theorem, I need to find two convergent sequence. Okay, any convergent sequence given here or not? Any convergent sequence that are given here? Any convergent sequence given? Only two lines, and you have only one assumption. Any convergent sequence there? No. AN? AN is the one we want to look for. Okay. I'm not sure how you're familiar with proving. Okay. So now this statement is like if P then Q. Okay. Q is what you want to find. Okay. Your job. This is your job. Your job to show. Okay. P is the one that's a given condition. Okay. You have P. But Q you don't have. You need to show. Okay. So the one those are given to you, is it convergent or not? Hmm? Okay, I'm not very sure about the definition of conversion. What is this notation here? I mean, huh? What's this notation here? Sorry? What's this notation? Absolute AN is what? Huh? Okay, wait. So do you know what the absolute value is? Huh? Let's recall this definition here. What is absolute value? Again, by definition, this is a function that gives you x if x is greater than 0, equals 0 if you include here, minus x if x is less than 0. Okay, so what is this trying to do? For example, modulus of 2 is what? 2. Okay, because 2 is greater than 0. Okay, modulus of minus 2 is what? 2. Why? Because it's less than 0. So I need to put minus 2, which is 2. Okay. All right. So I put modulus on AN. What does it mean? Okay. So at first I got AN, right? Okay. AN is what? AN is just a list of number. Remember last time I introduced A1, A2, A3, A4, A5, and so on. Okay, so what is absolute AN here? So absolute AN here just means I take absolute on every term. Okay, I make all of them positive. Is it still a sequence or not? Still a sequence, right? Okay, still a sequence. Okay. So this sequence converge or not? Converge to where? 0. Okay, so this is the content of this notation here. Limit of my sequence converge to 0. Okay. Okay. Does it make sense? This is definition. You cannot ask why, because this is definition. Okay, it is like that. Okay, this is our definition. So whenever we say so sometimes you will see me writing as an goes to 0 when n goes to infinity. They are the same thing. Okay, so they are the same. Okay. 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 So we got a convergence sequence which is absolute value of an. Okay. Uh, so an is what we want to find. And then absolute an is what we know. Okay. So can we? So I say I want to use Swiss theorem. So can we bound an with this convergence sequence or not? Yes or no? Right? So let me ask you, an greater or absolute an is greater? Huh? An is less than or equal to absolute value of an. Okay, that's very good. Does everyone agree or not with this? Does everyone agree? Because you make an positive already, right? Positive one still stay positive. Makes sense? For example, in our example here, -2 is less than absolute value of -2, which is 2. -2 is less than equal to. Okay. Okay. How about the other side? Can we bound below by something else? Yeah, just take the minus of absolute value of an. Okay. So you make everything below. Yeah, sure, we got this inequality already. But the sad case is we only know that the right hand side converge to 0. How about the left hand side? So who is saying? Yeah, what do you say? Why? Everything time for 0 is 0. What theorem is that? Huh? What theorem is that? What theorem are you using? So absolute an converges. How about minus of absolute an? You only have two tools in your hand now. Okay, three. Three. Okay. One is if you know the function converge, the sequence also converge. Two is the property of convergent sequence. Remember, said that the limit is a linear operator on the convergent, the space of convergent sequence. So you can take what it will call for you. You got a long list. This list you have to remember. Property of limits. Okay. So you know that constant sequence converge to that constant. And then you can multiply constant on your sequence, convergent sequence. And then what you get is just a constant times the limit of the original convergence of sequence. And you can add convergence sequence together. Okay, and then the result is just the sum of your limit. And then you can multiply the convergence sequence together. And then the result is just multiplication of the limit of the convergence sequence. And similarly, you can divide. Okay. So can you use this property to tell anything or not about minus absolute value of a? Which one can you use? Which side? What do you mean by both sides? You use the number 2. Number 2, use number 2. Okay, so now in our case here, AN is absolute AN. Okay, what is C? -1. Okay, so -1. So it becomes -1 times the limit of the absolute value. Okay, and actually you can also use 4. How to use 4? You can also use 4. 4 implies 2. How to use 4? Dn is -1, or you take An to be C, the constant. Okay, so you have C, and so. Okay. Limit of a constant function is just C. Yeah, so you can recover 2 from 4. So actually, I can throw away this one. Okay, I can throw away number 2. I can just keep number 4. 4 is more general than 2. All right. Yeah, let's go on. Let's go on. Are we? Okay. Next. Okay. So what did I say just now? So since we know that the absolute of AN converges, okay, to 0, okay, by property of limit of convergent sequence, okay, we know that limit n to infinity of minus absolute value of AN is equal to minus limit of n to infinity of absolute value of AN, which is just minus 1 times 0, which is just 0. Okay, so limit commute with scalar. Okay, if the sequence here is convergent. All right, so we know that the left hand side converges to 0, the right hand side converges to 0, then we can use squeeze theorem. So about the squeeze theorem, the middle limit converges to 0 as desired. Okay. Okay. So I rarely prove in class, but when I prove, that means that some technique is very important inside this proof. Okay, this technique will happen maybe in your assignment or your test. Okay. So you need to learn the proof. Okay. Unless I'll tell you some proof is not important, but this proof is quite standard. Okay, so after you prove it, remember how to use it. Okay, so if you happen to know that absolute value of AN converges to 0, and then AN also converges to 0. You can try some experiment. Is there anything special about this 0 or not? Can I change it to 2, 3, 4, 3.5, pi, anything? Does it still work? Why not?
Not convert to the same only. So we can know for the AN is included at the side is not equal to the same L.
You need to provide a counter example. Yeah. Okay, how about we take a break, you write down the example, and then we'll see if it's correct or not. And then if it's correct, then I will let everyone know. Okay? Yeah. Okay. Try to write it down first, because I don't want to spend time discussing. Okay? So yeah, you can think about it. Okay, everyone should think about it, whether we can change the 0 to any number else. If not, why? You just give me a counter example. Okay, just give me an example. Don't need to tell me why. Just give me a counter example. Okay, any question before we take a break? No? Okay, we'll take a break until 2:07 and then we'll come back. We'll resume. Yeah.
现在提到一个像我这样，能不能？
这句话没有写完，是不是？这句话停了。
啊，对对对，这句话。
OK OK，你要我看什么先？
就我这个主解法跟后面那个写法是都可以。我看到后面那个还要再讨论它是鸡还是？
哦，那一个是我要说的，这个东西是对的。哦，你是这个意思。OK OK，我只是想要，我只是想要证明这第一句是对的吧？对，就这样。
对，
因为你也没有解释第一句为什么对嘛，所以我就解释为什么第一句是对的。
因为像我后面这要写的很详细的过程。
对，因为对于他们是新的事，对啊，
这种是我们
我觉得呀，
他我们是几个题目里面选一个。
什么要几个题目选？
我看到我们只好几个题目里面选一个吧。
哦，对，你就选一个就好，写一个就行。
哪几个选？
就是从我们的课程里面，所有都可以，只要跟我们有关系，就是我班上有动到，或者说我班上的颜色一些都可以。
是 Project One 还是
Project
One？Project
One。对。
然后其他题目我看到这很多这东西都要变。
什么叫要变？
的那个 model 里面。
对。
是
啊。
跟我们后面有什么的关系吗？
有关系。OK，等一下我会再说一些。OK，我会介绍一些，因为太多我一下子介绍你们也。OK，等一下我会再说一些。OK。
不是说问你这样行不行，然后说我找到就行，我找到了。
你找到了，给我看一下。
他给的算第二章。
第二章。
Chapter 2的。然后我翻到的。
OK。
我就说他没有，就只要证他比他大，是吧
？OK。
我只是没来得及写。
OK，没错。对。OK。
哦，那也是会搞错。
搞错。
找一个比他小的，然后。哦，那个选的不对
啊！你看，
我选一个比他小的。
对，
就一个比他小就行。我这个选错了。
啊，你再试试。
便可以取代你的。那如果我用的是这个，
因为这个的时候，如果是等于的情况，当然可以了。但是如果你偶的另外一个情况就不行。
那就一个情况可以，一个情况不可以。
一个情况是永远可以，另外一个情况是不一定可以。
我如果就是要注意用。
呀。
就是在用就有这个情况下。
两边呀，如果你想要两边取里面的话，你就要小心一点了，或直接这样子调出来那个。
明白。是。
break。哦，现在也在 break 啊，070到07，还有8分钟。哎，我有算错吗？没有算错。刚才157 10分钟，207，还有5分钟。Yeah。啊？ Yeah.
I think for the example is for this one because if it's equal to x but because of the absolute, so unless x is bigger than 0. So because it will not become to 0, so I let x bigger than 0. So it's for this one we found out this one is equal to negative x, but this one equal to x. So it will become inside of negative y and x. But for the second theorem, we know that if
yeah, I mean you cannot use sequence theorem, but is the result still hold? You cannot say, oh, I cannot use sequence theorem, then this is wrong. Maybe I can use different way to prove it. You get what I mean? You can't just say that because this proof doesn't work, this statement is wrong. Maybe other proof will work.
Okay.
Right? So you need to really give me a counterexample if you think that is counterexample to the original statement. Does it make sense or not? Okay. The mean
the meantime, maybe I take attendance. 郭狂野6元，单金生 I think go toilet. 全家 is it 全家 correct? Okay. 全家 Ivan 老西赖西 sorry. Larry Kong 罗雷中一西桥东郑康AEC OK 尤罗山欧汉卫 OK 水逆 OK 安彦入辽若兰汉维国推了丹卓金陈宇翔 OK good your class is quite consistent OK
这是钱哦，
什么是钱？
就是要买哦，用这种还是有啦。啊，
我不是有放这边吗？哎，这里 textbook。
那我是看到题目吧？我是看到题目。
要看到题目。
我自己是没有办法，也是找不出来。
有啊，这是整本书啊。
这么我在只看
1000多面。
哦。我也都是答案，都是题目。
没有。哦，你是看到这些，啊？这个是前面罢了。你要看 Chapter 11。Yeah， 我们 start with Chapter 11。Calculus 2。前面应该是 Calculus 2。你们是用这本？
我们之前不是
用这本？
我在，我知道。
你我知道。
他们应该是，我也不知道你是独立教，
你们是也是
独立教。
呀，用这本。
这样子可以吗？没有。 I will see.
Okay. We should start now. Hey, where's Hanwei? Hello? Okay, I didn't introduce you, right? There's a lot of things inside these resources, but as I would say, Rome is not built in one day because last semester, we slowly add these things in. So yeah, some helpful website for you. This one is for later courses. Yeah, this one is extra knowledge for you because I found this is very interesting because the ancient Chinese also learned this calculus, but they put their variables in terms of Chinese character. You can have a look of this. This is coming from the Harvard Library, free download. Free download. Okay. I put some LaTeX help here, LaTeX guide or LaTeX symbol. And then this Beamer is for later for presentation for you to do the PowerPoint. Okay. So all the project you should use LaTeX only. Okay, no Microsoft Word or so on. Okay, just LaTeX. Okay, you can use the download the online version, which is Overleaf also can, but LaTeX. Okay, and I put few links here. Okay, so I put a journal of my name, calculus. So this is what are these actually? So these are the project by last year. Okay, so you have some reference to see what you should do. Okay, what kind of format I'm aiming for. You can have a look. And the apply one is for project 2. Okay, so don't look at this first. Look at these two first. Look at pure first. So project 1 is about pure maths. Project 2 is about applied maths. Okay, I mean real life apply. And then this presentation is last semester also. Okay, so you can choose their topics, but you cannot copy their content. Okay, you need to do your own research. Okay, so if you read their work, you think very interesting, I want to go on with this, or I just want to write this, both can. Okay, but you cannot copy or take their content. Okay, those content are written by them. They also digest the reference and then they write themselves. Okay, similarly, you should do that. Okay, if you really need to refer to their work, you also need to cite them. Good, clear? Okay, yeah. So these you can see what they did, and then this is what I wanted for a project. So I'm like training you to write some paper, okay, but not formal one, but informal paper, okay? A mini paper. Okay, do a mini paper. Yeah, if any more question, we can still keep discussing throughout the course, okay? Before the timeline. But your job now is throughout the lecture, try and find some interesting project you want to write on. Okay, let's continue. Okay, let's continue. So look at this example here. So we look at the sequence r to the power n, okay, where r is a scalar. It's some real number. Okay. So we want to ask, when does r to the power n converge? Okay, when does r to the power n converge? So maybe try some value for you, okay? So let's try r equals to 0. Okay. 0, what do you get? 0 to the power 1, 0 to the power 2, 0 to the power 3, 0 to the power 4, 0 to the power 5. This is just a constant 0 sequence, okay, which converges, obviously. So now I want you to try hands-on, okay? Try hands-on. Check for this value or other value. See whether you can deduce anything or not. When does this sequence converge? Let you try first, and then later we'll prove something. Okay, and you can check your answer with your friend. Okay, see whether they got the same answer, whether this value converge or not. Yeah, try check. Anything you observe? Did you get? Did you get anything? You get? What do you get? What happened? Converge? Converge to where? Okay. So numbers maybe in between -1 and 1 converge to 0. Okay. Anything else? Anything else? How about, so he only cover up to -1 to 1, right? How about -1? How about something below -1? Less than or equal to -1 and greater or equal to 1? Huh? No convergence. Everything no converge? How about I equals to 1? I equals to 1 is a constant, also a constant sequence, right? Okay, so this one converges to 1. Then other place should have no convergence. Okay, so we have to prove this. Okay, so we're just testing now. Okay, so let's claim this. So there's a claim here. Okay, so for I in real, okay, so we have a real line. Okay, it's always convenient to imagine the real line. So the only R that converges in between -1 and 1, including 1. Including 1. Okay. So just okay. Or make the summary here first, and then we will show it. So in between -1 and 1, okay, it is 0. And then if R greater than 1, it's diverging to infinity. If it is 1, it's just a constant 1 sequence. And for R less than equal to -1, it diverges. Anyone try -2, what happened? Huh? Jump up and down. Okay, jump up and down. So it like diverge to both sides. Okay. So let's prove it. So we need to prove one by one. Okay. So the easiest one is what I started off. When I equals 0, we know that it converges. Okay, converges to 0 because we always get a 0 constant constant 0. Okay. How about in between 1 and -1? Okay, what I do is I split it from r greater than 0 to 1. Okay, let's split it like this first. Why? Because this is true by your calculus 1 material. So if the number is bounded between 0 and 1, you take power of it, it converts to 0. Okay, look at the function Rx. Okay, how about the next one? Okay, you should notice now, if we go to negative, we will always have the jumping problem, right? Because when it is even, it's positive, or it is negative, and then we'll always have this jumping problem. So since we have this jumping problem, right, does R still converge or not within this range? Okay, does R still converge? Is it small enough to converge or not? Okay, is it small enough to converge? Okay, how are we going to show this? How are we going to show this? Just now we claim this conversion. So how to show? So we want to show limit of n to infinity of Rm is equal to 0. So how are we going to show this? We still have the jumping problem. Okay, but is it small enough to converge or not? Is it small enough? Can you imagine what I say? Can you imagine what I say or not? Right. So how should I draw it? So okay, how about let me just write down the terms. Let's pick r equals to minus 0.1 maybe. Okay, so r1 is what? R1 is minus 0.1, and then 0.01, and then minus 0.001, and so on. Okay, so how to prove whether this conversion? And as I claim that this converges to 0. So the jumping version, this is the jumping version of the sequence coming from R in between 0 and 1, right? The alternating version, okay? So any way that we can relate AN to the absolute of AN? Is there any way we can relate AN with absolute value of AN or not? Sorry? Minus. Oh, any Seng can relate this to, like how they converge. What's the result you want? You want AN to converge to 0, right? Okay. Do we know anything about absolute value of AN? Also converge to 0, right? Okay, this is by what we just established. Okay. So if we know the absolute value of AN converge to 0, do we know that AN converge to 0? Yeah. Why? We got the notes. Okay, we got the Swiss term. Yeah, the proof. But this is what we just proved before the break. Okay. If we know the absolute value of AN converge to 0, then AN will converge to 0. Okay. Okay. So what are we trying to do here? Okay. So what we have is we need to see whether. So we need to see we we need to see if lim n to infinity of absolute Rn is 0. Okay, so why is this the case that we have established? Okay, we need to explain why this is the same case as, okay, let me label these cases, otherwise you're confused. Okay, so we want to see why we can relate this to part 2. Okay, why we relate this to part 2. Okay, so this says that we need to make sure that we start with I between -1 and 0. Okay, we need to make sure that once we use this, our R will lie in between 0 and 1 to use the second result. Does it make sense? Okay, so we need to make sure that this is true. Okay, so what should we do? So what you need to observe here is absolute of Rn is what? It's just absolute of R to the power n. Does everyone agree with this? Agree? We can bring the power up. Okay, because Rn is absolute value of Rn is always positive. So you first take R to be positive and then you take any power you want. It's still positive. Okay? And then what? And then absolute value of R is always greater than 0 and less than 1. Does it make sense? Because R is in between -1 and 0. So you take absolute of R, of course you swap to the positive side. Yeah. Okay. So these two conditions here is exactly number 2. Okay. So you can see that I replace this R with absolute R at the bottom. Does it make sense? Okay. Or yeah. So actually I have nothing to say about it. I'm not sure you confused about what I say or not. No. How about the rest? Siying. How about Siying tell me? Okay, tell me how to use part 2. How to use part 2. How to use part 2 to show that the absolute of Rn converge to 0. You know how? You know how? You don't know? Okay. Yeah, please ask if you don't know. Okay. So the reason is here at the bottom here. Okay. I can write let me write more clearer. We need to see that if this is 0. Okay. So actually I should stop here. First, okay, we get limit of n to infinity of Rn. Okay, it's actually equals to limit of n to infinity of absolute of R. Okay, this one is okay because we got by the first equality here. These two are the same sequence. Okay, and then this is just 0. Okay, because we know that if the middle, the constant here is in between 0 and 1, we know that the sequence converges to 0. Okay, by calculus, 1. Okay. You can try to find this black box if you want. Yeah. Okay. Is everyone happy or not? Happy or not? Agree or not? Some agree. How about the other? Still blur. Please ask, Please ask. Okay. Okay, so once we establish the absolute value of Rn is 0, then the non-absolute version also 0, also convert to 0. Okay, this is by the I said proposition? Yeah, proposition just now. Okay, so by proposition before, we have limit and infinity of Rn go to 0 because absolute version of it also goes to 0. Okay, so you see, every proposition or theorem I introduce is not for fun one. Okay, because I want to use it later. Straight away I introduce it, I use it later. Okay, so every time take note when I introduce a proposition or theorem because I'm going to use it. Okay, so we won't do stuff for fun. Okay, we have to use it. We need to use it. Okay. Next, what have we covered? So we cover everything from -1 to 1. Okay, we cover everything from -1 to 1. How about we do 1 first? Okay, let's do 1 first. So let's do r equals to 1. So r equals to 1 is the same as similar to r equals to 0. You get where you get the constant function 1. Okay, so you get 1. Okay, now 2. How about r greater than 1? Okay. So r greater than 1, really, you also need to get the result from your calculus 1 also. So if you take positive power of a number greater than 1, you get larger and larger and larger. And for r less than or equal to -1, the limit of Rn doesn't exist. Okay, so I just put this word down. So how do you show that it doesn't exist? How do you show that it doesn't exist? To do it rigorously, we don't have the 2 because we don't have epsilon delta. But how to see it? How to see it is like how you determine, remember, how you determine -1 to the power n diverges. How you determine the -1 to the power n diverges? Because it just stay at -1 and 1. Okay, but this one is worse. This one is getting away from 1, getting away from -1 and larger. Yeah, this one is worse. Makes sense. Okay. Can you imagine what I say? Can I imagine? Okay, so let me try r equals to -2, right? Okay. Let's look at these two numbers here. Okay. Sometimes, right? Sometimes, if you can't understand what I say, you should ask me to draw it or explain it. Because I really meant what I say. Okay, so last time recall we have for -1 to the power n, what do we get? So we get like okay, let's label this first. So minus 1, 1, this, and then -1, 1, and then so on. Okay, how about -2? Okay, -2, what do you get? You get first term is -2, and then 4, -8, and then 16, -32. Okay, so what you get is you let's do it on the same picture, right? So you can really see what I say. So what I mean by getting worse, because you are getting away from the -1 sequence. So you start with -2, and then you get larger. So let me make this smaller. Okay, and then let me find this. So you got -2, and then 4, and then 8, very far away, and then far away, even far away. So this is what I meant by this. Okay. Okay. All right. Okay. So we can't be too precise on the part 6 because we don't have epsilon delta stuff. But if you're really interested in showing this, I suggest you can do it. You do it in your project. Okay, I can help you. Okay, yeah, because you see, so I said that doing projects benefit everyone, right? So if you do this, then all of you will learn it. Oh, this is the reason why I learned this. Okay, precise. Okay, instead of just me just hand waving, telling you this is true. Okay? Because for mathematics, right, we always want to get to the bottom. We have to get to the bottom. There's no gray area in mathematics. Either true, either false. Right? In proposition, you learn it's only true statement or false statement. There's no non-true, non-false statement. This is not proposition. This is not what we are looking for in mathematics. Okay? Yeah, only true or false. All right. Let me see. Yeah, let's do one more. Should we do one more? Or we should not? Let's see. Okay, so maybe we skip this. I left as a homework. You go back and do yourself. I will post up the solution for this homework. So this homework is find limit of n infinity of n factorial over n to the power n. Okay, n factorial over n to the power n. Okay. If you have any problem regarding this exercise, you can tell me or ask me or the next lecture or before next lecture, and then we can discuss together if it is too hard. Okay, so how about I let you guess a favor whether this converge. You have to guess whether this converge. Huh? Converge? Why? Or much bigger, okay? But always be careful about this much bigger thing, right? Okay, sometimes it doesn't work, but sorry. Enough big, yeah. So how much is enough, right? So this is very important. This is the thing we always. This is the place where we give new mathematics. You know, how much is enough? And so this is the gray part we can give new mathematics. So one comment I want to make is, yeah, you can use that to be your intuition, okay, your intuition to see. But sometimes you need to be careful because sometimes it's not big enough, okay. But in this case, it's big enough, okay. So you need to be able to show, okay, mathematically converge and then converge to what, okay. One hint I can tell you is try and use squeeze theorem. If you don't use squeeze theorem and then you found it, please tell me. Okay, it's okay. Don't always believe what I say. Okay, try your own method. Okay, I just give you an idea. Okay. So this one is your homework. So let's go to the new stuff. So I'm gonna introduce this theorem here. So suppose we have a sequence that converges, where a sequence converges, and then the function, okay, a function. This function might not have anything to do with our an, okay, some arbitrary function. It's a continuous function, okay, it's a continuous function, and continuous at this limit here at L. Okay, what's the result we get? Then limit of n to infinity of f a n is equal to fn. Okay, so this is a sequence definition of continuity. Okay, so how to find the limit of f applied to your sequence? It's just fl. Okay. In other words, what is this? Okay. This actually means that my limit operator go inside my function. Okay, commute with my function. Okay, commute with my function. This is the key point here. Commuting. Okay, you see this go inside here. Okay, so that the inside limit here is by assumption L. Okay, so this is the key of this definition. So what's the picture here? Okay, so I like to talk with picture, right? So let's do this picture business. Okay, so we have our graph here ready. Okay, we have our graph. So we have AN converging. Okay, AN is on the line X is the domain, right? We plug inside the domain of this function. Okay, it's lying on the domain. So we got A1, A2, A3, and then so on, and then converge to some number. Let's call it L. Okay, call it L here. So what happened to my function? Okay, this function I said that this is an arbitrary function. Okay, arbitrary function, but it's an arbitrary continuous function. What does continuous function mean? Real number. Okay, sure. Okay, good point here. This continuous function so far we define on real numbers. Sorry, real. Okay, domain is a real. Wait, let's say like that. Okay, so this continuity we define a function of real variable. Okay, real value, real domain. Okay, so what's the physical? What's that? How do you see continuity physically? How do you see continuity physically? Sorry. No stop. Okay. So you can draw the function with one pen without lifting your pen. Okay, with one stroke without lifting your pen. So it's continuous at L. So meaning you have to achieve somewhere in L. Okay. At other place, I don't know. Okay, but let's make it continuous. Okay, so so it is not allowed to have a. So in other words, it is not allowed to have a dot or jumping at L, okay, because it's continuous at L. So I have to fill in this jump here. Okay. So what is FAN? What is FAN? Okay, because function is defined for the domain. Okay, so you can apply function to AN, and that value you get is exactly this curve here. Okay, so you will get this curve here. Okay, and then so on. Okay, cool. So you have AN, you apply F. And so you got FA1, FA2, FA3, and so on. So FA1, FA2, FA3, FA4 form a new sequence, right? New sequence. So does this sequence have to converge or not? Have to converge or not? Does this sequence have to converge? Yes. Okay. A priori doesn't have to converge, but you are a continuous function. If you don't converge, later you will become something like a jump. Okay, so you must converge. Okay, converge to what? Okay, this is our problem. Always we want to answer. If you converge to what? Because you say already converge, right? So must converge to some finite value. So what's that value? Can we compute or not? Does it rely on some assumption or not? And then the theorem tells you just apply F to your L. Okay, you just apply F to your L. So this highest point here. So this highest point here is just F applied to L. Okay. L is given. F is given. Can you compute FL? Yeah, just substitute F equals to L. So you can get FL. Okay. Okay. So yeah. So I want to make a remark here. So what remark I want to make here? This is what I said a moment ago. So limit n to infinity commute with functions. Okay, not always, not always. Only under these conditions. Okay. So this condition is very important. If I don't have converging AN, then we don't know what's going on. If my function is not continuous, then I don't know what's going on. Okay. So this two piece of information is very important. Okay. So if you want to see why is it true, you can try and prove it. Okay. Try and prove it. Okay, so let's see how useful is this thing. Okay, let's see how useful is this. So we want to find limit of sine pi over n when n go to infinity. So let's see how we're going to use this theorem here. Okay, so to use that theorem, what are the assumptions in the theorem? You have a sequence, you have a function. Can you cook out some function and the sequence here, continuous function and sequence out of this sequence here? What what choice of an and f you can use? What choice? N use pi over n, fx use sine x. Okay, so there's few more things to check, right? My function have to be continuous at the limit of this sequence. So this sequence, is it converging or not? Okay. Is it converging or not? Huh? Converging. Converge to where? Okay, so this converge to 0 when n goes to infinity. Does sine x continuous at 0? Zero? Yes. Okay, sine s is continuous at 0. Okay, so in this case here, by theorem before, okay, by theorem above, limit of n to infinity of sine pi over n, what can we do? We can bring the limit into our function over n, which is sine 0, which is just 0. Okay. Actually, right. Actually, I suggest you to draw this sequence again. Okay, see whether you can see it converge to 0. Then you can try and draw it. Try and draw this. Try draw. Okay. So it's still got 5 minutes. Don't worry. Okay. Next. Next. Okay. Next. So just now I actually used some terms like bounded above, bounded below, but I never tell you what it means, definition. So let's introduce some more definition here. Okay. So first definition is an increasing sequence. Okay. So what do I mean by increasing sequence? Can you have a guess? What kind of sequence should be increasing? The number keep growing. Okay. So an is less than an plus 1 for all n. Okay. How about decreasing? an is bigger than an plus 1. Okay. Decreasing if an is greater than an plus 1. Okay, you can see that I use strictly, strictly greater, strictly less than. Okay, how about less than equal to or greater or equal to? Okay, for those cases, we will say a sequence, okay, is called non-decreasing. Okay, it is not decreasing. okay, if an is less than or equal to an plus 1 for all n. Okay. Next is a non-increasing. Okay, it's called non-increasing if an is greater or equal to an plus 1. Okay, so how you imagine this thing? So increasing, you should think of it as a keep going up, going uphill, and an less than an plus 1 is going downhill. Okay, how about non-decreasing? Okay, non-decreasing, you can think of it as a staircase. Okay, maybe you stay constant, go up, stay constant, and then non-increasing will be you go down, maybe stay constant for a while, and then go down. Okay, like a staircase. Okay, this is the definition, and can keep going on. So, next is the more important definition. So, a sequence is strictly monotonic if it is increasing or decreasing. Is monotone decreasing or increasing? And then we will say that a sequence is monotonic. Okay, is monotone. Strictly monotone. If it is non-decreasing, or non-increasing. Okay, so you can see that this strictly right is following our inequality, whether the inequality is strict or not. Okay. All right. Next, I want to finish all the definition here. So a sequence is bounded above. A sequence is bounded above. Two more definition, and then one theorem we will finish. If there exists a number m such that an is less than or equal to m for all n greater than 1. Okay, so if you can use a finite number to bound every term, then your sequence is bounded above, then your sequence is bounded above by m. Okay, similarly, we can bound it by below. Okay, so a is bounded below. If there exists another number such that every term is greater or equal to little m. Okay? So we'll say that a sequence is bounded. Okay, so if it is bounded, then it is bounded above and below. Okay, if a sequence is bounded above and okay. So why we introduce all these things? So let's introduce the theorem, and then we'll stop, and then we'll come back to the theorem again. So the theorem is called the monotonic sequence theorem. So this is by far the most important theorem. So every bounded monotone sequence is convergent. Okay. Every bounded monotone sequence is convergent. So you can think of these staircase, uphill, downhill. Okay. So if you bounded above and below, so the idea is if you bounded above and below, okay, for your terms, because your term is keep growing, okay, keep growing, but you are bounded above and below. So somehow you must meet the ceiling, or you must meet the floor. Okay. But does the floor or the ceiling have to be your limit? This is a question I want to throw to you. Okay, so if you keep increasing, if you have a ceiling or you have a floor, if you keep decreasing, does the limit have to equal to the floor or ceiling? Okay, I might answer, I might not answer. Maybe I'll put into test, or maybe I'll put into assignment. Okay, see whether how you think about it, and you can let me know. Okay. Okay. If no question, we will finish.
对，那个 homework，
Yeah，
我的想法是这样的，因为看到了阶乘，我就想能不能把它上一项比下一项，因为阶乘不就能约掉很多。
OK，
然后我就想到，因为 an 是大于0，那如果我证明 an 是 decreasing， 那我能说 an 一定在缩减于
这样你就要用到我们这个东西。
对，
你就要用这个，你就要用这个，对，你就要用这个。你可以试一下。
那如果这样的话，应该就比较好做。
你有了这个部分，你需要这一部分才会。
然后我还有另外一个想法，就是因为我先猜想它是缩减于0嘛，然后那我想我能不能证明它 an 的和 convert to 一个值，然后对，就比如说这样子，那如果我能证明 an 的和等于一个值，
可是这一个好像我们不知道。
对，我就这么一想，这个有道理吗？没有道理。
这个想象，但是后面那个不是你想要的东西，对不对？这个不是你想要。
对，这不是我想要。
对呀，然后你要这一句，为什么？
因为如果我能证明后面的话，就能说明前面是正确的。
不能，if P then Q 只能够有了 P 有 Q 不能够 implies P， 除非你是 if 这个 then 这个。对，对。
那这个可以吗？
哪一个？
就是我现在这个想法。
让我们出去说。